Welcome viewers, this is Mr. Odingo. I welcome you to this lesson so that we try to look at something more about isotopes. Last time we were able to explain that isotopes are atoms of the same element that have different neutron numbers but have the same proton numbers. Today I want us to move on to relative atomic mass of these particular isotopes. I want to invite you to understand, if you're a chemistry student or you are new to chemistry, one way or another you have seen the periodic table. And when you look at the periodic table, like the other day I invited you to go to check what we call atomic symbols. If you look at a periodic table, you realize that some of the mass numbers in the periodic table are decimals. The question is, we know the mass numbers is obtained by adding the number of protons and neutrons in an atom. So how then can we get a decimal point? Because we know a neutron has a mass of 1, a proton has a mass of about 1 atomic mass units. So where does the decimal come in? This is the result, this is what brings up the decimals. For example, if we have rubidium with atomic mass 85, and atomic number 37, that's rubidium 85, and then we have rubidium 87. So rubidium 87, we have mass of 87 and atomic number of 37. If we have these masses here, these are the two isotopes of rubidium, two naturally occurring isotopes. How do we get the relative atomic mass? Because in the periodic table, we have to put one rubidium. We are not going to indicate two of them. Now there are two. We saw magnesium in our last lesson had 3 isotopes. But in the periodic table, we only have one position for one magnesium. So it means that for us to be able to deal with that particular problem, we need to get the average mass of these rubidium atoms. And as such, we are going to look at what we call the relative abundance. The composition. If we have a container full of rubidium atoms, we know that in that particular container, some rubidium atoms will be rubidium 85, some will be rubidium 87. And these rubidium atoms, they don't exist in that particular container in equal proportions. One has more atoms than the other, and that's why we call it what we call relative abundance. And in this case here, rubidium 85 is about 72%, and rubidium 87 is about 28%. So if you look at this particular atoms of rubidium, we know that these rubidiums will be more than the other one in that particular container. Why? Because this one has a higher relative abundance than this one. If you look at chlorine, for example, chlorine has 2 isotopes, and chlorine, we have chlorine 35 and chlorine 37. These 2 isotopes of chlorine, they also have different percentage compositions in existence. For example, chlorine 35, if you have a container full or a gas jar full of chlorine gas, in that particular container, you will find that 75% of the chlorine gas inside that container is carrying chlorine 35 atoms, and 25% of chlorine gas in that particular container carries 25% of chlorine 37. That is what we mean by relative abundance or relative compositions. They are never 50-50, and none is 100%. So today we want to look at what is the relative atomic mass. We say relative atomic mass is the average mass of one atom relative to 1/12 of the mass of carbon-12. Carbon-12 has been used as the standard atom to measure the masses of these particular isotopes. So we give these masses relative to that one to 1/12 of the mass of carbon-12. And what do we say average mass? It's not just the way average mass, but we should use the word weighted average. Why is it weighted? It is weighted because we need to take into consideration the percentage compositions. Because if this one carries 75%, this one carries 25%, it's very illogical for us to just say the average is 35 plus 37 over 2. If I do 35 plus 37 divided by 2, this will be wrong. Why? Because they can't share equally, yet chlorine 35 is more abundant than chlorine 37. That is why we have a special way or special formula to use when we are calculating this particular masses of isotopes, relative masses of isotopes. And the formula here, it means that we have to multiply the mass number of the isotope 1 times its relative abundance. And that in case is here, if I want relative atomic mass of chlorine, gram of chlorine, I'll say it is 35 times its relative abundance, which is 75, plus chlorine 37, the mass number is 37, its mass there, 37 times its relative abundance, which is 25. Everything here we divide by 100. So we say that if you want to get the average mass, the relative atomic mass, the word relative meaning we have to compare. We have to bring in that element of comparison using the percentage abundances which are given to us here. We don't just say 35 plus 37 over 2, assuming that is 50-50. Here we have 75, we have 25. So we have to take the mass number here times the percentage, the mass number here times the percentage, then everything, because the total percentage is 100%, everything divided by 100. And according to my calculation, I will get 35 times 75 plus 37 times 25. The total I will get here is 33,550. 3,550 divided by 100. I divide by 100. I get 35.5. 35.5. This is the relative atomic mass. This is the relative atomic mass of chlorine. And this mass here, we don't have units because relative atomic mass is a ratio. So we don't indicate any unit. It is just a number, 35.5. Viewer, I want us to go to another example. And this example now, I want it to be a little tricky. And because examiners are not easy people. We have isotopes of magnesium. We have protons. We have neutrons. We have electrons. So we have a table here. These are isotopes of magnesium. So these isotopes of magnesium, examiners are people who think far, and they will always want to do something to make life hard for you as a learner. So protons here are 12. Here are 12 in isotope 1, isotope 2, isotope 3. Here need 12 as well. Neutrons here 12, 13, 14. Electrons are 12, 12, 12. And then you are told that the percentage abundance of this isotope here, percentage abundance, this one is 79, this one here is 10, this is 11. So we have isotopes here. This time we don't have mass numbers, but believe me, viewer, we can get the mass numbers. One mass number here we can calculate by adding. We know that the mass number of isotope 1 will be protons, which are 12, plus 12, which will give us 24. So the mass number of isotope 1 is 24. We go to isotope number 2, the mass number is 12 plus 13. Remember, electrons here are indicated just there to confuse you. You are not supposed to use them at all. So this will be 12 plus 13 for isotope 2, which will give us 25. Then finally, we have isotope 3 of magnesium, which will be 12 plus 14 equals to 26. So now we have the mass numbers of each isotope. We have 24, the relative abundance is 79. 25, the relative abundance is 10. 26, the relative abundance is 11. So we can now get the RAM. The relative atomic mass of magnesium will be the mass number times the relative abundance, which is 79. plus 25, the second one, times 10, plus 26 times 11. Everything, as we said in the first example, divided by 100. So viewer, we can do the math quickly so that we get the answer. That is 24 times 79 plus 25 times 10 plus 26 times 11. According to me, the answer is 2,432. I divide everything by 100. And what I get here is, divided by 100, I get 24.32. Viewers, this is how far we can calculate this particular atomic numbers. I started by giving you chlorine, which had got mass numbers. Then we came to magnesium, where we just have protons and neutrons. So for us to get the mass number, we really have to add ourselves before we can be able to calculate the relative atomic mass. Viewers, lastly, I want to show you something that is very common in examination, but students really don't understand how to answer this particular question. And you may meet in exams anytime. This question tells you, I want to use an example of neon. Neon, we have neon 20 and neon 22. These are the isotopes of neon. Neon 20 and neon 22. Then examiner tells you that if you have neon 20 and neon 22 as the main isotopes of neon, but then the relative atomic mass of neon is 20.2. In this particular case, the examiner has calculated for us the relative atomic mass. Then we have the mass numbers of neon 20, we have the mass number of neon 22. Then you are asked, examiner asks you that, what is the most abundant isotope? Is it neon 20 or neon 22? In other words, which one has the highest percentage composition? For us to be able to answer this question, we have to compare the relative atomic mass with the mass number here and with the mass number here. We have to check this relative atomic mass number. Which isotope is it closer to its mass number? For example, between 22 and 20.2, then compare 22.2 and 20. Which mass number, which number here is closer to 20.2? And from my judgment, I can do a little math and say that if I tend to subtract 20.2 minus 20, I will get 0.2. That's the difference. But if I come here, 22 minus 20.2, I will get 1.8. So the difference between this relative atomic mass number and this number here is bigger compared to this and this. So the most abundant isotope in this particular case is neon 20, because its mass number is closer to the relative atomic mass number, atomic mass of that. So if you are asked in examination which one is the most abundant isotope, you say neon 20 is the most abundant because its mass number is closer to the relative atomic mass. Thank you, viewers. That is the end of our lesson today, and tune in next time so that we can continue learning together.